Okay, like I said, today is laying the groundwork leading up to our big day of the unit circle. The first part of that is you're going to hear this phrase called reference angle, or sorry, standard position show up in some of your problems where it talks about an angle being drawn in standard position. What does that mean? Well, it means the same way we've been drawing all of our angles. One of the sides of your angles is the positive x-axis. And then it talks about this terminal side of point x comma y. Okay, well, an ordered pair for a point is x comma y. If I were to connect that point back to my origin, the angle you just formed with the positive x-axis is called an angle in standard position. All of our angles will be drawn in standard position. If we think about ordered pairs, how do each of those ordered pairs get us to the different quadrants that we will have in our axis? Quadrants 1, 2, 3, and 4. To move into quadrant 1, I would move to the right, which is a positive x value, and up, which is a positive y value. To move into quadrant 2, I have to move left. Well, left is a negative x value, which means the first number in my ordered pair would be negative, comma, positive y value. To move into quadrant 3, I would have to move left, which is negative, and down, which is also negative. So both my x and my y values would be negative. And quadrant 4, I move to the right, which is positive, and down, which is a negative y value. So just reminding ourselves of how we learned how to graph a point and how I end up in each of the different quadrants. This chart that you see up here, sine of theta equals y over r, cosine of theta equals x over r, do not spend a second memorizing that. In fact, we will just reference this, and you'll only need to reference it for a couple problems over the next 2 days. When we get to Thursday, this chart becomes obsolete. So have it in your notes. We will reference it, especially when we start looking at an axis and we can't draw a triangle. But I think a triangle is actually the easier way to attack these types of problems. If we were to look at a point x comma y, if I start my pencil at the origin and I trace my way to that ordered pair x comma y, going to the right x, up y, if I connect back to the origin, it will always create a right triangle. If we draw it that way, we know how to do our 6 trig functions looking at a right triangle. Most of you just showed me that on your quiz yesterday, right? So if we draw the right triangle, I would say go through what you know SOHCAHTOA to do your trig functions. Don't memorize this. We'll reference this in a couple pages here. But this is what you're going to do. When given a point 2 comma negative 4, drawing a right triangle where theta is at the origin. Theta will always be at the origin. You're going to do this. Start your pencil at the origin, okay? Trace to this ordered pair the same way you would. So if it's a positive 2, that means to go to the right 2. A negative 4 means go down 4, so I would trace that. I would go to the right 2. I would go down 4, okay? And that puts me to that ordered pair 2 comma negative 4. Connect that point back to the origin and put theta as the angle at the origin, always. Okay, so just start at the origin, trace the correct order, to the right 2, down 4 to get to that ordered pair. Now, a couple things that I will note. Once we have that started, your right angle's here, if you want to draw it in there. But to find our missing side, you will do your Pythagorean theorem, just like we've always done. It will always be your hypotenuse on this type of problem. The other thing is this, and they call it r in these problems. Your hypotenuse is r. Why, I'll tell you in just a second here. But it is also always positive. It does not matter which quadrant you're in. The hypotenuse r of your triangle will always be a positive number. Why do they call it r? If I were to find some point over here, yeah, if I were to trace to that, this distance right here, if I were to draw the circle through that point centered at our origin, this distance is your radius, which will always be the hypotenuse of that right triangle. That's why your book refers to it as r, okay? And that's where we get into our unit circle eventually, is all focused on that segment length right there. So, okay, so let's look at a problem that actually has a question that starts like this. Let negative 4 comma 3 be a point on the terminal side, where it stops, of an angle theta in standard position. Find the exact values of the 6 trig functions of theta. Okay, so job number 1 is to draw a picture of this triangle that has that ordered pair on it. So I'm going to trace my way to -4, 3. Start at the origin. -4 tells me to go which way? Left. So I'm going to go left 4, and then I would go up 3 and connect back to my origin. So I'll show you that again. Start at your origin, trace your way to the ordered pair. Left 4, up 3. Just don't pick up your pencil, and then connect back to the origin. Theta always goes at the origin. Okay? To find our hypotenuse, we do Pythagorean theorem. Don't let your calculator lie to you. Remember that anything squared always turns out positive. If I type in -4 squared incorrectly, it might try to tell me that it's -16, right? But -4 squared is just plain old 16, which sometimes means doing it in my head might be easier or safer. 9 plus 16 is 25. Now, when I square at something, technically I do get plus or minus, right? But because of where this number is going on my triangle, I know it's the positive because the hypotenuse is always positive. The radius is always positive. Okay. Now, once we have that drawn, again, I am not using this little chart up here. I am looking at this as a right triangle just like I would have yesterday, where I identify the fact that this is theta, makes 3 opposite, -4 adjacent, 5 my hypotenuse, and I set up my SOHCAHTOA here and do my reciprocals there. That has not changed. Okay, so let's get those set up. So that should be old news for us. Sine is opposite 3 over hypotenuse 5. Cosine is adjacent -4 over hypotenuse 5. Tangent opposite over adjacent 3 over -4. Turn those upside down for my reciprocals. Cosecant is the reciprocal of sine, 5 over 3. Secant is the reciprocal of cosine, -5 over 4. Cotangent is the reciprocal of tangent, -4 over 3. The negative doesn't matter where it is, as long as you've got one of them in that fraction, it's the same thing. Okay, questions so far? Try drawing one on your own here, and then I'll help you finish out the triangle and get to our 6 trig functions. But it says let -3, -6 be a point on the terminal side of your angle in standard position. So what I want you to do is draw that triangle, work on your hypotenuse. Radical. Again, start your pencil at the origin, trace to that ordered pair. -3 should have told you to move left 3. -6 means move down 6. Connect back to my origin. Your triangle should look just like mine. -3, -6 were the directions I went to get to this point. Theta is always at our origin. And just Pythagorean theorem to find my third side, just like we've been doing with any missing third side of a triangle. So -3 squared plus -6 squared equals r squared. -3 squared is 9. -6 squared is 36. 9 plus 36 is 45. It did say exact. So a reminder on the whole exact thing, I do have to simplify my radicals, not get decimals, right? So what is the biggest perfect square that goes into 45? 9. So my missing side would be 3 square root of 5, always positive. It doesn't matter what quadrant it's in, the hypotenuse is always positive. Okay, setting up my trig ratios, all based off of where theta is. Theta is always at the origin, which makes the 3 the adjacent side, the -6 the opposite, the 3 square root of 5 your hypotenuse. Set up your Opposite over hypotenuse would be negative 6 over 3 square root of 5. Adjacent over hypotenuse, negative 3 over 3 square root of 5. Tangent, opposite over adjacent, negative 6 over negative 3. Now, I purposely put the original ratio up there. Not done, though, right? We always have to simplify fractions, and can't leave those radicals in the bottom, right? We do have to rationalize. So finishing this out, first of all, 6 and 3 would simplify down into 2 over 1, and rationalize by multiplying by square root of 5, top and bottom, and we would get an overall answer of negative 2 square root of 5 over square root of 5 times square root of 5 is 5. Good. Same thing here, your 3's would cancel, rationalize. Negative 1 times the square root of 5, and then square root of 5 times square root of 5, so we'd get negative square root of 5 over 5. And again, it doesn't matter where the negative is as long as you have one of them in that fraction. In the bottom, negative 6 over negative 3. Negative over negative is a positive. 6 over 3 is 2. I would, again, just giving you a little hint, go back to the unsimplified fraction to do my reciprocal, because you'll have to do less work. If you go to the simplified where you rationalize, you're going to have to rationalize again. So I would go back over here and turn that upside down. 3 square root of 5 over negative 6, and then I can just simplify the numbers. 3 over 6 would simplify down into 2 over 1, or negative square root of 5 over 2. Turn this one upside down, 3 square root of 5 over negative 3. The 3's cancel, negative square root of 5 over 1, which I don't have to write over 1. And our last one, turning 2 upside down, or turning that one upside down, would be 1/2. Any questions? So we're moving on from this topic. Okay. The next part is what happens if the angle that they give me, or the point that they give me, lands me on an axis. This is the one and only time that you guys are going to use that little chart that I had on there a couple slides ago. And eventually we won't need that at all because we're going to get to our unit circle and get some other options. So what type of angles will land me on an axis? They have them up here, but I'm going to draw them on my own as well. If we are talking angles, remember that in degrees, that we are always going to be in increments of 90. So starting at 0, anything that's a multiple of 90, 180, 270, 360, anything that's a multiple of 90 is going to drop me on an axis. If I get over a full circle, just keep adding 90 again, 450, add 90 again, 540, add 90 again, 630, and we could keep going if we needed to. But those numbers would drop me on an axis. If we are talking in radians, the numbers that are going to drop me on an axis, 0. Now we are used to talking about this being 1 pi and this being 2 pi for a full circle. But what if I only go half of the way? That puts me on this positive y-axis. Well, that'd be half of 1 pi, or pi divided by 2, pi over 2. Which means every axis, kind of like when we're adding 90s over here, we're adding pi over 2s. 1 pi over 2, 2 over 2, 1, right? 3 over 2 puts me down here. 4 over 2, which would simplify down to 2, would put me over here. Now, if we went past that, we can just keep adding pi over 2. So that would be 4 over 2, 5 over 2, 6 over 2, 7 over 2, 8 over 2. Every line that we add, another over 2. If it's ever over 2, it's going to put you on a positive or negative y-axis. If it's ever a whole number, it's going to put you on a positive or negative x-axis. 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. Any whole number lands us on one of those x-axes. Okay, so if it lands us on an axis, this is what I want you to reference. Those are all supposed to be zeros up there. I don't know why one of them's smaller. But it's talking about, okay, what would a generic point look like that would put me on that axis? Some number, comma, 0 would put me on the positive x-axis. 0, comma, some number would put me up there on the positive y-axis. Negative some number, comma, 0 would put me over here, and 0, comma, negative something would put me down here. We're going to think through those ordered pairs, again, just for a couple days as we work our way up to the unit circle. And that's where we're going to also use that chart that I gave you on the first slide. and these ordered pairs to be able to come up with whatever trig function they ask us to look at, okay? All right, so combining that with the chart that we had earlier, and a question like this, cosine of pi. They're only going to ask us for one trig function. It's going to give us an angle, and that angle is going to land us on an axis. Pi, let me do a different color here, would be the angle that goes right here. So we'd be talking about this angle right here. That's the point that it would go through. So what I want you to look at is what ordered pair corresponds to what axis we just fell on, which would be negative r comma 0. That is your x comma y. And then I want you to go to the chart and look at which trig function they're asking you for. They're asking you for cosine. So the combination of this ordered pair and the fact that they say that cosine of theta is x over r, r will always be r. And then in the fraction, you're going to go to the ordered pair for your x's and y's. So if we want the cosine of pi, cosine is supposed to be x over r. At pi, here's your ordered pair. So my x value is negative r. R is always r. And negative r over r would simplify down to what? Negative 1, right? I don't know what r is, but a number over itself simplifies down to 1, right? And one of them was negative. So our answer would be negative 1. Okay, we're going to do 2 more examples like this, and then we can look at questions if this is not making sense. Okay, so let's try another one that's going to put us on an axis. I want you to think about for a second where the angle 450 would put you. Knowing that it's going to put us on an axis, right, because that's this whole section right here. Which axis do we end up stopping at if it's 450 degrees? When we're talking degrees, think in increments of 90, right? So I start at 0, go to 90, 180, 270, 360, add 90 more, we get up to 450. So the angle 450 would look like that. That's the ordered pair we would use for that point, 0, comma r. And they ask us to do tangent of that angle. Well, the tangent of an angle is the ratio of the y value over the x value. Remember, our ordered pair goes x comma y. So the tangent of 450 degrees, x over y, go to your ordered pair here, would be r over 0. If I have something over 0, what does that fraction simplify down to? Undefined. Undefined. Okay, so that's a big note for yourself right here. If 0 is in the bottom, our fraction simplifies down to undefined every time. Yep. Correct. Always. And eventually, as we start doing our unit circle, you're going to start recognizing those more and more. Like I said, kind of building our way up to the unit circle, but that's always going to be true about that angle. All right, let's do one more, and then we will kind of recap this section. Cotangent of 7 pi over 2. Your job right now is figure out what axis 7 pi over 2 is going to land us on. Anything over 2 will land us on an axis. You just got to figure out which one. Okay, before we get too far into this, let's make sure we all ended at the same axis. A couple slides ago, we talked about thinking radians and how far we move for each line. And remember that each line is going to move us another pi over 2. 1 pi over 2. So as I go, that would be 1 pi over 2, 2 over 2, 3 over 2. And how far was I supposed to go? 7. So that's 3, 4, 5, 6, 7. Did you guys all get down to that bottom y-axis? I'll do that again. 1 over 2, 2 over 2, 3 over 2, 4 over 2, 5 over 2, 6 over 2, 7 pi over 2 puts us down here. That's the ordered pair I should be using. Cotangent I get from my chart for right now is our x value over our y value, and we're about to see our last option here. Our x is 0. Our y is negative r. If the 0 is in the top of the fraction, that simplifies down to what? 0. 0 divided by anything is 0. So there's your last option. If 0 is in the numerator, it will equal 0. Guys, there's only 3 numbers you can get for this. 0 in the top of the fraction, we're going to get 0. 0 in the bottom of the fraction, we're going to get undefined. If both of them are an r, we're going to get 1, negative or positive 1, depending on if those are negative or positive in there. But that's your only options. If it's on an axis, you can't get anything else. 1, negative 1, 0, or undefined. Any questions on that? Okay. Shifting into our last kind of topic here is dealing with reference angles and how that's going to help us, again, building up to our unit circle here. A reference angle is this, and this is what your book uses, and I'm going to talk through this, but then we're going to talk about, okay, let's talk in real world here, how am I going to find reference angles? First of all, a reference angle is this. This is the symbol for it, not something you necessarily need to know really well, but it's theta prime. It's the angle formed by where you stop your drawing and the closest x-axis. Now, you guys see my notes all the time. If I have something written this big, do you think it's important? Yeah, right? Notice it doesn't say y-axis. You will never use the y-axis. The only options are numbers from your x-axis. So let's talk through this, what the book does and these little formulas it gives you. You're not going to memorize formulas. We're going to talk about, okay, real world, how do I find my reference angle here? But this is what it looks like. If I had an angle big enough to drop me into quadrant 1, 45 degrees, okay? My reference angle would be going back to that original x-axis, and you would be the same distance away from that as your angle is. So if my angle was small enough to be in quadrant 1, like 45 degrees, its reference angle is 45 degrees. We'd be 45 degrees away from 0, okay? Now, if my angle was big enough to put me into quadrant 2, like 120 degrees, my closest x-axis becomes this guy over here, which would be 180 degrees. And so the formula they give you is that you would take 180 minus your angle, or pi in radians, minus your angle. If my angle is big enough to put me into quadrant 3, your closest x-axis is still this one over here, 180 degrees, but now my angle is bigger than 180 degrees. Well, notice on the formula, they switch it. Instead of saying 180 minus theta, they say theta minus 180, our angle minus 180. Why do they do that? Well, a reference angle is actually your distance to the closest x-axis. Distance is positive. It doesn't matter how we got to our angle or which direction we're talking. Distance is positive. I wouldn't say that we're going 2 miles to Elkhorn High and negative 10 miles to Gretna High, right? Distance is positive no matter which way it's going. A reference angle is always positive. If my angle were big enough to put me into quadrant 4, my closest x-axis would be finishing out a full circle. Well, a full circle is 360 degrees or 2 pi. So you see that it is 360 minus my angle or 2 pi minus my angle. Let's say my angle was 300 degrees. That would put me into quadrant 4. The closest x-axis would be 360 degrees, making my reference angle 60 degrees. So in degrees, that is 180, 0, or 360. That's all you can use. You cannot use, these are not options. You cannot use your y-axis or your y-axis. In radians, that is 0 or 2 pi and 1 pi, and I would put those in terms of whatever denominator we have, okay? So we're going to practice a couple of these. I think it'll make more sense when I go to this next picture here. Let's start with the negative 150 degrees. Start by drawing yourself that picture. First of all, negative means we're going to head down first. We think in increments of 90, so there would be 90. The next 90 would put me at 180, so I would stop before that. there is a picture of negative 150 degrees. My closest x-axis would be this guy right here, is 180 degrees. Now, your reference angle is the difference between those. Positive and the negatives make no difference on this. How far apart are 150 and 180? 30. Doesn't matter the fact that we got there in a negative direction. It doesn't matter that it's less. None of that matters. Your answer is always positive. Always, always, always positive. Okay? Questions on that? That's your answer. Reference angle. How far are we? And it's building us to our unit circle. So it's going to make more sense eventually. Actually, in a couple slides, it'll help us out a little bit. Good? So far? Okay, let's look at the next one. Switching to radians. So again, to draw my angle, I think in terms of the denominator, 4 over 4 and 8 over 4. 3 pi over 4 would be just short of 4 over 4. This is going to put me somewhere in here, right? Okay, now think in terms of the numerator. They've got the same denominator. This is 3 pi over 4. I need to get to 4 pi over 4. How short am I? 1 pi over 4, right? So my reference angle would be pi over 4. That's how far it is to my closest x-axis. Now, on that first page I said using 0 or 180 or 360 was your only option. Yes, but we kind of have to adjust for this a little bit because we're bigger than a full circle. So as I draw 520 degrees, actually kind of talking through it might help you figure out your reference angle. That's bigger than a full circle, right? So I'm going to go with the 360 to start with. And then we start working in increments of 90 degrees. So if I were to go 90 degrees more, that would be 450. 90 degrees more would be 540. Well, I'm only supposed to go to 520. Okay, well, this is an easy one. How far are we then from our closest x-axis? 20 degrees. The mistake people are going to make is they're going to go to a y-axis if the y-axis happens to be closer. You will never use a y-axis. Horizontal lines. Where is your closest x-axis? Okay, you and your table partner can work on this together. I'm going to give you about a minute or two to think on this. This is what I want you to do. Draw me each of those angles and find me their reference angle. And if you get done before we get all that up there, you're going to find me the shortcut. That is going to be the reason that you guys love radians over degrees. Because someday you're going to like radians more than you like degrees. Maybe not today. After I show you the shortcut, you might start to like them. We'll get there. You did not butcher that. Yeah.
I know that sounds stupid.
Nope. And nope. We're going to simplify it even more than that. I don't even want to do that much work. Okay. Again, getting these drawn correctly, focus on the denominator. Think about the fact that this is 6 pi over 6. Again, eventually, guys, you're not going to have to draw that. And some of you are to that point already. If you aren't, keep drawing the 6 and the 12. Help yourself visualize this. If I'm supposed to go 7 pi over 6, 6 over 6 is a half a circle, so I need to go just past that, right? That would be my 7 pi over 6. How far away am I from my closest x-axis? We'd have to go backwards, which is fine, but our answer is still positive. Positive what? Pi over 6. We're at 7, and I need to go back to 6 pi over 6, okay? Again, think in terms of my denominator. I like this one because it's got the negative in there, so I'm supposed to head the negative direction. More than a full circle, right? Because negative 8 over 4 would be a full circle, so negative 9 over 4 is going to go just past that. The signs, and this is why I don't love the whole memorizing the formula behind it, because negatives and stuff start making it weird. How far are we from our closest x-axis? Pi over 4, right? We're 1 away. 8 pi over 4 would be your closest x-axis. We're at 9 pi over 4, so 1 pi over 4 away. Same thing with our pi over 3s. 3 pi over 3, 6 pi over 3. I need to go 2 pi over 3, which means I can't even finish half a circle. Okay. How far away am I? Pi over 3. Okay, I want this super simple. What's your shortcut if your angle is in radians for its reference angle? Pi over the denominator. That's it. So if they hand me an angle that is 7 pi over 6, what's your reference angle? Pi over 6. If they hand me an angle that's negative 9 pi over 4, my reference angle, pi over 4. Same thing, pi over 3. So do I need the 2 in there? Well, yeah, because that's going to tell me which quadrant it's in, which is going to make a difference to us eventually. But that is super simple for finding my reference angle. It's going to make finding numbers in your unit circle a lot faster too. All right, our last topic here puts all these things together. This is just from your book, but it talks about, okay, well, utilizing that reference angle, and then drawing in our special right triangles here, which I will remind you of, can get us to trig values, to get us to right triangles when it's not an angle that like falls into our first quadrant. Back in geometry, you guys spent like a chapter on special right triangles, and now it's been a while, so I'm going to do a quick reminder of what those were. Special right triangles were triangles who were either of the format 45 degrees, 90, or 30, 60, 90. These two are the same, just turning different ways, okay? And what it turned out is that the sides always ended up with the same ratios. And we're not going to go through all of that today because that was what you learned back in geometry, but what were those ratios? In 45, 90, it was an isosceles, two angles the same, right? Two sides the same. Your legs were like x, x, and then the hypotenuse was the x times the square root of 2. Does that look familiar to anyone? Okay. Now, I don't care if you call it x, x, x square root of 2, or 1, 1, 1 square root of 2, or leg, leg, leg square root of 2, whatever's going to work best for you. They're going to simplify out of there anyway, so you just need the same thing. On your 30, 60, 90, it was all based off of that 30-degree angle and the side across from it. That's what we based our triangle on, is that side being called x. The hypotenuse was always double that length, and the side across from your 60 was that length times the square root of 3. Now, the reason I have it drawn twice, I will use this one when the angle that's at my origin is the 30 degrees, or pi over 6 is the same thing as 30 degrees. Okay. I'll use this model if the angle that's at my origin is the 60 degrees. It's the same model, just twisted for you. So across from my 60 degrees is that x times the square root of 3. Across my 30 is the x, and my hypotenuse is still 2x. Okay. Now, these are all done in degrees, but understand what that matches to in radians. If I were to get a reference angle of pi over 4, that's the same thing as 45 degrees. I set up this triangle. If I get an answer of pi over 6 for my reference angle, I set up this triangle. A reference angle of pi over 3, I set up this triangle. Okay, so let's see these in action. How am I going to utilize those? I'm given a question like, find the value of sine of 4 pi over 3. First of all, we learned, what is the reference angle for 4 pi over 3? Pi over 3, right? The 4 helps me figure out where to draw this. So think again in terms of my fractions, 3 pi over 3, 6 pi over 3. Figuring out which quadrant 4 pi over 3 goes into is very important. 4 pi over 3 is going to put us into quadrant 3. Okay. Now, I already asked this, so I will reiterate. When I asked you what the reference angle is, you told me pi over 3, right? We're going to mark that in our picture. That's this angle here is pi over 3. Back to my closest x-axis. Put a dot at the end of that angle and trace your way to that dot. Start back at your origin. I would have to move to the left and down, and that has now completed that triangle for us. This reference angle is a pi over 3, so as I'm getting used to this, I'm going to flip to this page in my notes. I'm going to say, find where it says my reference angle is pi over 3, and draw those ratios. So across from that pi over 3, across from that 60 degrees, is my x squared root of 3. Across from my 30 degrees, which is this guy down here, or my pi over 6, is x, and my hypotenuse is 2x. This is where you have to slow down a little bit. Which direction did I move on each of those? Because they might need to be made negative. This guy moves left, which means that's a negative value. This guy moves down, which means that's a negative value. Your hypotenuse will still always be positive. Good so far? Okay, now we've got our triangle. In that triangle, here's my angle, which means this is my adjacent side, this is my opposite side, this is my hypotenuse side, and they ask me to do the sine of 4 pi over 3. Well, sine is opposite over hypotenuse, right? So go to your triangle and put the ratio of the opposite over the hypotenuse. Negative x squared root of 3 over 2x. Simplify. Okay, well, what's going to happen is those x's will always simplify out of there. My answer, negative square root of 3 over 2. Questions? Okay, let's try another one. Tangent of 150 degrees. Draw me the angle, find the reference angle. That's where we are always going to start this. Draw the angle, find the reference angle, and then we'll create our special right triangle around that. Okay, 150 degrees should put me into quadrant 2. What's my reference angle? How far am I from my closest x-axis? 30. That's what we base all of this off of. So 30 degrees. Draw yourself a triangle to the end of that. So start back at your origin. I would have to move left and up. There's my right triangle. Okay. And 30 degrees was at my origin, so I come back here, find the one that is 30 degrees at the origin, use that special right triangle model. Across from my 30 is x. Across from my 60 is x times the square root of 3. My hypotenuse, which would be over here, is 2 times x. Think about which direction I moved. This guy is moving left, so it's negative. This guy's up, positive. Hypotenuse, always positive. Set up the ratio they ask me for. So they ask us to do, what, tangent? Okay, well, tangent is opposite over adjacent. Use your angle at the origin to label your sides. Opposite over adjacent would be x over negative x squared root of 3. Two things, your x's will cancel and rationalize. So we get the square root of 3 times 1 in the top over, we got that negative on there, square root of 3 times square root of 3 is 3. Negative square root of 3 over 3. Okay, we haven't done one with our 45, 45, 90. So let's look at one more example that uses that 45, 45 model. Secant of 15 pi over 4. 15 pi over 4, that's a big angle. Okay, so think in terms of the denominator, 4 pi over 4 and 8 pi over 4, and I have to get to 15 over 4. Full circle is going to be 8. Another 4 would put me up to 12. If I were to add another 4, I'd get up to 16, and I'm supposed to stop at 15. So I would be just short of 16 over 4. That would be my 15 pi over 4. Okay, that's 15 pi over 4. What's my reference angle? Pi over 4, right? That's the easy part. How far am I from my closest x-axis? In radians, it's always pi over the denominator. We learned on the last page that pi over 4 is the same thing as 45 degrees. So I'm drawing this special right triangle model to the end of this triangle. I would go right and down. There's my 45 degrees, which means it is x squared of 2. Just try that again, x squared of 2. Which I'm just copying that model onto my special right triangle there. Check which direction we moved. We moved right, which is positive. We moved down, which is negative. So make that x a negative. Hypotenuse is always positive. And I'm supposed to set up secant. Well, secant is the reciprocal of, which one? Cosine. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So looking at this being my reference angle, this would be adjacent, opposite, hypotenuse. So adjacent, hypotenuse over adjacent would be x square root of 2 over x, and simplify. Well, my x's are going to simplify out of there, leaving me with the square root of 2 over 1, which is just square root of 2. Questions?
So will we ever see one that doesn't have pi over the denominator? Is that just
Not in radians.